So let's welcome Erin Walker, who is the Associate Professor in the School of Computing and Information at the University of Pittsburgh. Her presentation is about robots as social learning companions. Okay, Erin, please.
Hi, everybody. I'm just going to go ahead and share my screen. And does that look good to everybody? Oh, I have to do it. I have to go back and do it with audio. One sec. Okay, there we go. That should be good. So welcome. I'm so excited to speak to you today. I am an associate professor at the University of Pittsburgh with a joint appointment in the School of Computing and Information and the Learning Research and Development Center. And I'm going to talk to you about the work that we're doing designing intelligent robots for classrooms. So a lot of the time when people think about the use of robots in education, they're thinking about our robots as tools approach, where learners build and program robots. And there are so many benefits to this approach. So for example, they get hands-on experience working on engineering and computer science problems. These activities tend to be inherently engaging and rewarding for many learners. And learners learn to see themselves as creators of technology, which can be really empowering for their future career paths. But there's another way that robots can be used in education, and that's as an intelligent learning companion. So in this robots as companions approach, learners are taught by an intelligent robot, or in some cases, they even learn alongside or teach a robot. So this is also inherently engaging for learners to interact with a robotic companion. And furthermore, it leverages benefits of collaborative learning because people are often interacting with these robots using natural dialogue, and potentially most importantly, it can enable the personalization of learning experiences directly to learner needs. So because these robots are intelligent, they can design learning experiences that adapt to learner prior knowledge or their preferences, that sort of thing. And so in my lab, we've been looking very broadly at how we design robotic companions to foster student learning. And we've had three focus areas that I'm going to talk to you about today. So one of them is designing social behaviors into the robot. Another one is using the robot to foster collaborative scenarios. And then another one, the last one, is combining the robot as tools and robot as companions approach by adding programmable features into an intelligent social robot. So I'm going to talk at a very high level about all three of those approaches. So the first project that I'm going to talk about involves examining what happens when you add social behaviors into a teachable robot for middle school math. And my team that I was working with is down below. I did want to say that Nicola Lubold spearheaded this work when she was a PhD student when we were both at ASU. So this project took a learning by teaching approach, where we were interested in leveraging the benefits of learning by teaching by have students teach a robotic companion. So when one student explains something to another student, it can improve their domain knowledge. They're explaining their reasoning, they're fielding questions, they're trying to understand what the other students know, and they develop this really deep understanding of the domain, even if they were not previously an expert in that area. So it has a lot of benefits when you're teaching another person, and it's been found that human interactions with intelligent agents has similar benefits as human-human teaching. And so we built this teachable robot named Nico for middle school math and specifically for ratio and proportions. So middle schoolers teach this robot using natural language dialogue about ratios and proportions. And I'm going to show this demo video for how Nico functions. Hopefully the audio comes out okay.
I really want to go swimming with my friends, but I need to put some waterproof paint on first. I need help figuring out how much paint to put on my legs and torso. Can you give me a hint for how to figure out the first part? Step 1?
Okay, Nico, so remember the ratio of 6 to 2, okay?
Okay, I will remember the ratio of 6 to 2.
So what is 12 divided by 6?
12 divided by 6 is 2.
What is 2 times 2?
2 times 2 is 4. So do we use the ratio between the 6 and the 2?
Yes, because 6 times 2 is 12. Therefore, 2 times 2 is 4.
Okay, I will put the answer as 4.
So you can see that the student explains to Nico how to solve the problem. Nico's asking questions, it's explaining its own reasoning, and eventually it takes its own steps in the problem by filling it out on the table. And what we were really interested in was understanding how Nico's social, verbal, and paraverbal behaviors might foster increased rapport between the learners and Nico, and then how that increased engagement, increased connection might influence learning outcomes. So our hypothesis was that if learners felt more of a connection with Nico, they might be more engaged in the task and ultimately benefit more. And so to do this, we implemented social dialogue in Nico. So you can see in this example on the left that Nico's doing things like complimenting the learner and using inclusive language, like using we instead of I. And then we also built social paraverbal behaviors into Nico in the form of pitch entrainment. So Nico's pitch converged to the learner's pitch over the course of a problem. And this mimics what happens between people as they're getting along. Whereas people are talking, if the conversation is going well, their speaking style becomes more similar to each other over the course of an interaction. And then we ran a study where 69 middle school students taught Nico in 1-hour sessions, and they were randomly assigned to one of 3 conditions. A condition that had the full profile of social behaviors, so pitch entrainment and social dialogue, a condition that just had the social dialogue but not the pitch entrainment, and then a condition that had no social behaviors. And we found that students in the entraining plus social condition, the full social condition, learned the most about math from a pre to post test. And also some evidence that the more social the condition, the more rapport students experience for the robot. And we ran a couple other studies with this paradigm with similar results, more rapport, better learning effects. And so we have some evidence here that combining different modalities of social interaction in a teachable robot enhances the experience for learners. And I think there's still a lot of areas to drive toward in order to really understand how social behaviors influence learning, like how we model social behaviors, what combinations of social behaviors are effective, and then how should we tailor the social experience to individual students. So in our studies, some students really enjoy the social experience, and some students would rather interact with a less social robot, but that's not captured in what we're doing. But I think we're well poised now to address these questions. And then the next project that I'm going to talk about is how we can use robotic learning companions to facilitate collaboration between 2 students. So this is also a teachable robot project. This is a screenshot of a pilot we ran during the pandemic, and we have 2 students here teaching our robot over Zoom, who we're now calling Emma. And our hypothesis is that if 2 students collaborate to teach the robot, it's going to combine the benefits of human-human collaboration, where people are having this really deep conversation surrounding the problem domain, with human agent interaction, where students are more engaged because they're interacting with an agent. And so we're doing this ongoing exploratory analysis where we ran a pilot with 14 undergraduate dyads, taught Emma ratio problems over Zoom in 90-minute sessions. So this was run during the pandemic, so it was over Zoom. And we're currently exploring these questions of individual differences. So how do group dynamics predict outcomes of interest? So for example, the more similar students' prior knowledge, the more they perceive rapport with Emma and with each other. So the better the interaction tends to go. And on the other hand, we saw evidence of pretty asymmetrical interactions where some groups had one student dominating the interaction or had students simply alternating between explaining problem steps without interacting with each other. And so now we're building into Emma the capacity to actually facilitate the collaboration. So we've implemented a version of Emma where she randomly calls on one student or the other and gaze at the student that she calls on during the course of the interaction. And we're now collecting data to understand how Emma's referencing influences the student interactions in the moment, with the ultimate goal of learning a reinforcement learning policy to do that referencing. So I'm going to show you a video from a middle school pilot that we did. This was in person. And you can see in the video that Emma's referencing does have an immediate effect. So when we start the video, student A has been leading the interaction, but then Emma starts referencing student B.
Take that number and multiply it by 3 because 15 times 3 is 45.
So is this a multiplication problem? Student B, so what do we do?
We take the total cost multiplied by 3.
We take the total cost and multiply it by 3.
We can just multiply $32.25 by 3. How do you know we can do that?
Because 15 times 3 is 45. So we could do the same thing to the other side.
Because we know that 15 times 3 is 45, so we have to do that to the other side.
If we have 3 times as many hot dogs, it will cost 3 times as much.
Yes.
Yes, correct.
So then 3 times $32.25 is $96.75. Student B, is that how much it will cost?
Yes, correct. That is the total cost.
Sweet. I will put the answer as $96.75.
So in some ways, this isn't ideal because the interaction between student A and student B is still very asymmetric. But in other ways, the referencing is leading student B to get more involved in the interaction and take more ownership over the problem solving. And so our next steps here are to use this data to learn a reinforcement learning policy for when to reference particular students to improve the balance of participation, but also to explore other kinds of facilitation actions that may engage a student like student B more deeply in the interactions. And so here in this project, we're exploring questions like how can the robot intelligently facilitate collaborations between groups of students, and how these facilitation strategies might change based on individual and group characteristics. And we're hoping by applying a method like reinforcement learning, we can learn from the data how these facilitation strategies need to change depending on the composition of the group. And then the last project I'm going to talk about is the effects of adding programmable features to a social robot. And instead of being in the context of middle school math, this is in the context of a middle school computer science program, actually teaching about computer science. And a lot of the thinking I'm going to talk about in this presentation was led by Dr. Angela Stewart. So we're exploring the use of a social programmable robot within the context of a broader culturally responsive curriculum. And the idea is we can't learn about technology without thinking about who designs it and who benefits from it. So the goal of a culturally responsive curriculum is to promote technosocial change agency, where learners are empowered to leverage, customize, and build technologies to affect positive change for themselves and their communities. And we're following Dr. Kimberly Scott's paradigm here. So in our curriculum, learners switch between reflections on power and identity, community building activities, and meaningful technology-related tasks like programming, with the idea that you can't learn about programming in isolation. You have to learn about it in the context of how technology is used in society and how it affects people and their communities. And so as part of this curriculum, we've created an agent, Simi, that's both social and programmable. Simi is also an artifact of the pandemic, so now we're moving to working with hummingbird robots here, but during the period that I'm going to talk about, we were using a virtual agent. And so Simi is social, like Nico and Emma, so it can have conversations about the learning content. Right now, those conversations are menu-based and somewhat keyword-based, but we're moving towards a more sophisticated dialogue system. But Simi is also programmable. So students can program Simi's movements, for example, like moving Simi's left arm. And students can also program more sophisticated behaviors into Simi, like its dialogue. So they can actually influence Simi's social behaviors. And the idea is that the addition of this programmable component is a natural fit for teaching about computer science and AI, because it sets up a context where learners exercise agency during interaction with the robot. They can customize and affect their robot behaviors. On the other hand, this combination of programming and social interactions allows for reflective conversations too about what design choices are made, what the effects might be, and who's affected by them. So it allows us to situate the programming in a broader context and in the context of reflections on things like power, identity, and community. So to learn about what this means, we ran some co-design sessions. So we had 15 middle school girls participating in 5 participatory design sessions, exploring what form a social programmable robot might take. And in many ways, the girls wanted to make the choices for how their robots should look, what their personality should be. So that screenshot on the left is an example of a robot learner design. She was saying, I was thinking the robot would be a bit sassy, so I chose the eyes that looked annoyed. But on the other hand, the girls recognize that allowing robots to decide their clothes, how they act, preference for name, gender, who they make friends with is a way to express themselves. So all of this is a marker of how agents, intelligent agents, people express themselves, and recognizing that on the part of the robot too. In the end, our participants preferred to give robots a limited amount of agency as long as they remained in control over the robot's tasks and functionality. And I think this gives us a blueprint moving forward for how to implement these social programmable robots, where for the most part, participants are customizing these robots, are programming these robots, but on occasion, the robot might ask a question or even challenge the decision in a way that causes everybody to reflect more on identity and on who gets to make these kinds of design decisions. And so we're exploring here, how should social programmable robots be designed? And then what are the learning benefits in engaging with social programmable robots? And I'm thinking specifically for teaching about computer science, for teaching about AI, but both in terms of what's traditionally considered core domain concepts in that area, but also how technology functions in the context of society. So I talked about 3 projects, looking at social behaviors, facilitation of collaboration, and adding programmable features as ways of designing robotic companions to foster student learning. I like to end these kinds of talks with a quick discussion of the ethics of robotic learning companions. So I think some things that we're striving for in our projects is making sure that the behaviors of our intelligent companions are transparent, so that it's clear why they're making the decisions that they are. And this yields agency to the learners in deciding how to use them, and helping, we think it's really important to facilitate them in customizing their experience with these companions. And then also these companions can be used to promote AI literacy, even when they're in contexts, when they're being used to teach about math. And this is an important component, we think, of empowering people to make informed decisions about how AI is used in their lives, including in their educational lives. But overall, I think robotic companions have a lot of potential to make an immediate positive impact in a multitude of learning contexts. So thanks very much. And I'm happy to take questions during the discussion section.
Great, thank you very much, Erin. So I thank you and thank, I guess it was Nico and Emma for their participation. We appreciate what they do.